Hi students, in this session we are going to discuss about some important topics regarding the LTI systems, linear time invariant systems. Okay, in that first I am going to discuss about systems with and without memory. Systems with memory and systems without memory. Okay, first I will go with the memoryless system, that is without memory. So memoryless systems are also called as static systems. Here memoryless systems are also called as static systems. Okay, a system is said to be a static system or a memoryless system. Memoryless system if output at any time, if the output of the system at any time depends only on the value of input at that time. If the output of the system at any time, depends only on the input value at that time, that is the output depends on the present input, then those systems are called as static systems or memoryless systems. There is no need to remember or anything. There is no need to remember anything. So there is no need to have the memory. Hence they are called as memoryless systems because the output depends on the present input only. So the output depends on input at that time is present input only. Okay. A continuous time LTI system is memoryless system if the condition is impulse response h of t will be equal to 0 for t not equal to 0. First I give the general definition. So if I want to say system as static system or the memoryless system, its output depends only on the present input. So if I want to explain that in terms of an impulse response, so for that I have considered an continuous time linear time invariant system. A continuous time LTI system is said to be memoryless. A continuous time linear time invariant system is said to be memoryless if the impulse response of the system h of t will be equal to 0 for t not equal to 0. So whenever the impulse response h of t will be equal to 0 for t not equal to 0 of a system, then we can say that system is a memoryless system. Okay, simple. There is a system, and for the system the impulse response h of t equal to 0 for t not equal to 0, then I can say the system is an memoryless system, and it is of the form y of t equal to k into x of t. That is, y of t is the output and x of t is the input. If we treat like this, then the output will be equal to some constant into x of t. So that is, output will be equal to some constant into input. Some constant, that is multiplied input, will give the output. So because the output depends on the present input, the output value is t, then the present input is also t. So it depends only on the present, not on the past or the future. Okay. So for that reason I have written y of t equal to k into x of t. For some constant k, so here the k has some constant, here for some constant k, y of t will be equal to k into x of t, and the impulse response h of t will be given as, so impulse response is the output of the system for an unit impulse as input. That is, whenever y of t equal to h of t, that is x of t will be equal to del of t, because h of t is the impulse response, that is the output. Whenever we give the input as unit impulse, here del of t is the unit impulse. So in place of y of t I can write h of t, then in place of x of t I can write del of t. So h of t will be equal to the constant k into del of t. H of t equal to k into del of t. Simple. The impulse response will be given as k into del of t. Okay. If h of t is not equal to 0 for t not equal to 0, then the continuous time LTI system has memory. The memory systems are nothing but dynamic systems. A memory system is also called as dynamic system. Or memory system. Dynamic. They can change according to the situation. Okay. So there the output depends on not only the present but also on the future or the past. It will change according dynamically. Okay. So if h of t is not equal to 0, h of t, that is impulse response of the system, is not equal to 0 for t not equal to 0, for t not equal to 0, the continuous time system will have a memory. Memory systems are called as dynamic systems. So memory systems are called as dynamic systems. So here we have two types of systems, static and dynamic. Static system is nothing but memoryless system. Dynamic system is nothing but memory system. So for a continuous time LTI system is said to be a static system or memoryless. The impulse response h of t will be equal to 0 for t not equal to 0. And if a continuous time LTI system is said to be a dynamic system or the memory system, its impulse response h of t is not equal to 0 for t not equal to 0. Okay, and in general this will be in the form of y of t equal to k into x of t. If I want to write the impulse response h of t, then h of t will be equal to k into del of t, because impulse response is the output of the system for a given unit impulse as input. For a given unit impulse as input. Finally, so in this equation, if k equal to 1, then h of t equal to del of t. If k equal to the constant equal to 1, then h of t equal to del of t. That is, the system becomes an identity system. Then the system becomes an identity system, because both the impulse response is same as the impulse input. So impulse response is same as the impulse input. That is, output is same as the input. So we can call that system as an identity system. We can call that system as an identity system. So this is about systems with and without memory, or simply we can say that is static and dynamic systems. So static systems are memoryless system, dynamic systems are memory systems. This is the explanation about static and dynamic systems. Okay, I already explained you about all the classification of systems in the first unit very clearly. So here I am giving the outlines and I am giving what will be helpful in this unit. Okay, so I am explaining this classification of system, that is static and dynamic, and then causality, stable, causal system, stable system, non-causal system, all this with respect to LTI systems, linear time invariant. Now I am explaining all the classification system, that is I am explaining static, dynamic, causal, non-causal, stable, unstable, and invertible, non-invertible, all this with respect to the analysis of LTI systems. So in this, first I gone with the static and dynamic, or simply systems with and without memory. Then I go for causality, and after that I will go for stability. At last I will finish with the invertibility. Okay, now we are moving on to causality. Nothing but causal system. Causal system. Okay, a causal system is non-anticipatory. Is non-anticipatory. It does not anticipate anything. It is a non-anticipatory and does not produce an output. And does not produce, that is a causal system, does not produce an output before an input is applied. Before an input is applied. That is, without applying the input, it does not produce any output. Those type of systems are called as causal system. A causal system is a non-anticipatory system. It does not anticipate anything. Okay, and it will not produce an output before an input is applied. So it will produce an output only after applying the input. That is simply, that is, for a causal system, the output depends only on present and past values, but not on the future inputs. So a continuous time LTI system is said to be a causal system if its output depends only on present and past values. So the output depends on the present and past values of the input, but not on the future inputs. That is, the output of a system depends on the present input or past input, but not on the future inputs. Then I can say those systems are called as an causal LTI system. Causal LTI system. Okay, simple. So a causal system is non-anticipatory and does not produce an output before an input is applied, and here the output depends only on the present and past values of the input, but not on the future inputs. Those type of systems are nothing but causal systems. For a causal LTI system, if it is a causal LTI system, the impulse response h of t will be equal to 0 for t less than 0. Very, very important. For a causal LTI system, the impulse response h of t will be equal to 0. If the given system is a causal system, then the impulse response of the system is 0 for t less than 0. If the t values are negative, that is less than 0 negative values, for that the impulse response will be equal to 0 if the system is a causal LTI system. The same way, a non-causal LTI system is anticipatory. Here, causal system is non-anticipatory, a non-causal system is anticipatory, and the impulse response h of t is not equal to 0 for t less than 0. For t less than 0. Here we have only two important points. The first point is the causal LTI system. For causal LTI system, the impulse response h of t equal to 0 for t less than 0, and for a non-causal system, the impulse response h of t is not equal to 0 for t less than 0, and the causal system is non-anticipatory, whereas non-causal system is anticipatory. And I have given the output of an causal signal given to a causal system, non-causal signal applied to a non-causal system, and non-causal signal applied to a causal system. Okay, I had already given you the 4 different combinations regarding this causal signal and causal system. So if you want, you can write those equations here also. Okay, already I explained those equations. For that I am not explaining again these equations here. Okay, this is nothing but about causality. Okay, simply the output depends on the present and past values, but not on the future inputs. First point. And h of t equal to 0 for causal system for t less than 0, and h of t is not equal to 0 for non-causal systems where t less than 0. That is, for t less than 0, h of t is not equal to 0 for non-causal systems. For t less than 0, h of t equal to 0 for causal system, and this causal system is non-anticipatory, whereas non-causal system is anticipatory. Okay, this is regarding causality. Next we move on to stability. Stable system. Stability. So a system is said to be a stable system if every bounded input produces a bound output. If I want to say a system as a stable system, if I want to say a system as a stable system, if every bounded input produces a bounded output, every bounded input produces a bounded output, then I can say the system is a stable system. Bounded input produces a bounded output. Bounded input BI, bounded output BO. So BO stable. BO stable, we call it as a BO stable. Simply, the BO stability of an LTI system is the BO stable. The BO stability, the stability of an LTI system, the stability of an LTI system is determined from its impulse response. That is, we can determine the stability of the system from its impulse response. So the BO stability, bounded input, bounded output stability of an LTI system is determined from its impulse response. So if we know the impulse response, from that impulse response we can say that whether the system is stable or not. Here, for a continuous time LTI system to be BO stable, that means if I want to say that a continuous time linear time invariant system is to be a BO stable, its impulse response must be absolutely integrable. That is, if the impulse response of the system, LTI system, is absolutely integrable, then I can say this is a BO stable system. Simple. If the impulse response of the given system is absolutely integrable, then I can say that the given system is a BO stable system. That is simply integral minus infinity mod of h of tau d tau will be less than infinity. Less than infinity means it will have a finite value. Integral minus infinity mod of h of tau d tau. H of tau, that is h of tau, that is nothing but the impulse response. So the impulse response must have a finite value. Finite value is less than infinity. So I can represent that in the equation format as integral minus infinity mod of h of tau d tau will be less than infinity. Okay. So if the equation satisfies, then I can say the system is an BO stable. Simple. If the impulse response is absolutely integrable for a continuous time linear time invariant system, then I can say that system is an BO stable system. That is, if the system satisfies the equation integral minus infinity h of mod of h of tau d tau is less than infinity, then I can say the system is a BO stable system. Simply, for a bounded input, it has to produce a bounded output. For every bounded input, it has to produce bounded output, then I can say that as a stable BO stable system. Okay, this is regarding stability. And the last one is invertibility. See, a continuous time LTI system, a continuous time LTI system with impulse response h of t. Let us consider a continuous time LTI system with impulse response h of t. Okay, if I want to say that continuous time LTI system with impulse response h of t is to be invertible, if I want to say it to be invertible, it is to be invertible system. If I want to say that as an invertible system, if an inverse system, there I have to need an inverse system with impulse response h1 of t. There I need an inverse system with impulse response h1 of t, which when connected in series with the original system, produces an output equal to the input of the first system, produce an output which is equal to the input of the first system. Very, very important. So if I want to say a system as an invertible system, okay, if the system has an impulse response h of t, then I need an inverse system with impulse response h1 of t, which is connected in series with the system having impulse response h of t, that is original system. So here I need two systems. The first system will have an impulse response h of t. See the diagram. So the first system, it is having an impulse response h of t, and I had considered another system with impulse response h of t, and I connected this in series with the original system. If the output of the second system is equal to the input of the first system, if the output of the second system is equal to the input of the first system, then I can say the system is an invertible system. So this is the block diagram representation of an invertibility system. Okay, simply that is equal to x of t will have an identical system. That is y of t equal to, or h of t equal to del of t. That is, here the impulse response will be equal to del of t. Identical. That is, identical means whatever the input I will give, that will be get at the output. That is, at the output I will get whatever the input given to the system. So if the x of t input is given to an identical system, then the output of the system will also be x of t. Simply. Okay. For this, actually, I have to consider two systems. The first system with an impulse response h of t, and the second system with an impulse response h1 of t, and I have to connect these two systems in series, and the output of the second system, that is the inverse system, is equal to the input of the first system. The output of the second system is equal to the input of the first system. Then I can say that system is an invertible system. Or simply, I can write the equivalent of this complete system as x of t is given to an identity system, then the output of that system is also will be equal to x of t, which is nothing but input. Okay, identity system whose impulse response will be equal to del of t. So for an identity system, we know that for an identity system, h of t impulse response will be equal to del of t. If you consider those type of systems, then I get the output which is as input. That is, I get the output same as input. Okay, this is nothing but about invertible system. So first of all, I had given the input signal to a system with impulse response h of t, and the output of the first system is given to another system with impulse response h1 of t. The output of that second system having the impulse response h1 of t is same as the input of the first system, that is x of t as shown in the diagram. Then I can say the system is an invertible system. So that is the block diagram representation of invertible system. Or simply, that is equivalent to x of t is given to an identity system, then I can get the output same as input, that is output is also equal to x of t. Okay, this is regarding the invertibility. Okay, so here I discussed about the four topics. The first one is static or memoryless, or we can first one static or memoryless, both are same, and second one dynamic or memory systems. Okay, simply we can call this the first topic as systems with and without memory. So the first topic is systems with and without memory. The second one is causality, and third one is stability, and the last one is invertibility. So I hope these four things are clearly understandable to you. So here everything I explained with respect to LTI systems and with respect to impulse response. Here the main concept is around this impulse response, h of t. So everything here, all the concepts are linked with the impulse response. Hence the impulse response plays a major role, okay, for finding the behavior of the systems. Okay, so this is about the causality, stability, invertibility and systems with and without memory. Okay, now we will discuss about two topics. The first one is a step response, a simple unit step response, and then I will explain you about the topic transfer function of an LTI system. Transfer function of an LTI system. So in this two first I am starting with the unit step response. Unit step response. So the unit step response of an LTI system is nothing but the output of the system. Output of the system for a unit step input. For a unit step input, that is u of t. So here for a system, if you give input as u of t, that means for the system the input is unit step, that is u of t. In that case the output of the system is nothing but the unit step response, that is s of t. Okay, s of t. Here for this, here I consider a system, and the system I take the input as u of t. Input as u of t. Okay, so for a system, if I given the input as unit step u of t, then the output of the system is nothing but the unit step response, that is response output. So output of the system for a unit step input. Okay, simple, there is nothing but the unit step response, and this unit step response is obtained by the convolution of, by convoluting the impulse response with the unit step, by the convolution of impulse response with the unit step. So simply here we will represent the step response with s of t. We will represent the step response with s of t. So the step response of the system is obtained by the convolution of unit impulse response h of t and unit step u of t. So the convolution of unit impulse response h of t, simply the convolution of impulse response h of t and unit step u of t will give the unit step response, or this can be written as u of t convolution h of t, that is a convolution of unit step with the impulse response. Okay, now the step response s of t will be equal to the formula, so integral minus infinity to infinity. So here we have to go for causal and non-causal different systems. Based on that we can write change the limits according to the given system. Okay, in general we will take s of t equal to integral minus infinity to t h of tau u of t minus tau d tau, See, we substitute the values of t minus t 0 less than t, there is a positive value. So minus 5 t minus of minus 5 t plus 5 u of plus positive value. So u of value for t greater than 0. So u of some positive value will give 1. Positive value will give 1. So h of tau into 1 is h of tau. So finally I got the unit step response, or simply step response s of t will be equal to integral minus infinity to infinity, or simply we can write it as minus infinity to tau minus infinity to t h of tau d tau. So s of t will be equal to integral minus infinity to t h of tau d tau. Okay, so we can write like this: s of t equal to integral minus infinity to t h of tau d tau, and this h of tau, or simply we can write as h of t. H of t is the impulse response. So impulse response is nothing but the first derivative of this step response, because step response is the integration of impulse response. So impulse response is the first derivative of the step response. So if I know the step response, I can find out the impulse response. So the step response can also be used to characterize an LTI system. Generally, impulse response is used to characterize the system, because system behavior will be obtained from impulse response. Here impulse response is obtained from step response. So step response can also be used to characterize an LTI system. Why? Because here impulse response is characterized by the step response, or impulse response is obtained by the step response. So step response can also be used to characterize an LTI system. Okay, this is regarding unit step response. Simply output of the system for a unit step input. Output of the system for a unit step input is nothing but the unit step response. Okay, and here it is an integral. Simply convolution of, it is convolution of impulse response and unit step, and you apply the convolution formula, and the limits of this convolution, the limits of the integral are according to the given systems. So for different systems, for causal system we have different limits of the integral, for non-causal system we have different limits. So in general I had given the case of step response as integral minus infinity tau h of tau d tau. Okay, so this is regarding step response. Now we move on to the transfer function of an LTI system. Now we move on to the transfer function of an LTI system. Okay, so here I consider a system. Here I consider a system with impulse response h of t, with impulse response h of t, and Laplace transform of that one h of s, and Fourier transform of that one h of omega. Simply h of omega is the Fourier transform of h of t, and h of s is the Laplace transform of h of t. So we consider with respect to h of t or h of s or h of omega. In these three I can consider with any one of these. So I consider a system with impulse response h of t, and the input signal is x of t and the output signal is y of t. Input is x of t, output is y of t, and the input spectrum is x of s, input spectrum in s domain, and input spectrum in frequency domain is x of omega. The same way output spectrum in s domain is y of s, output spectrum in frequency domain is y of omega. Simply here x of t, h of t and y of t will form a set. So these three will respect to one thing, x of t, h of t, y of t. So in s domain we will consider x of s, h of s and y of s, and in frequency domain we will consider x of omega, h of omega and y of omega. These three will form a set. Okay, so this is the simple representation for a block diagram for explaining the transfer function of an LTI system. See here, the transfer function of an LTI system is defined using Fourier transform or Laplace transform. That is, the transfer function of the given system will be defined using Fourier transform. By using Fourier transform or by using Laplace transform, we can define the transfer function. This is under zero initial conditions. So we will define all these under zero initial conditions. I have to set that initial conditions as 0, neglecting the initial condition, that is 0 initial conditions. Okay, now see what is the definition of this transfer function. The transfer function of the LTI system, the transfer function of LTI system, the transfer function of LTI system is dependent with h of omega. Here this h of omega is the transfer function of the LTI system, and that will be given as y of omega by x of omega, or simply the transfer function of LTI system is nothing but the ratio of the Fourier transform of the output signal to the Fourier transform of the input signal. Ratio of the Fourier transform of the output signal, that is Fourier transform of y of t, to the Fourier transform of the input signal, that is f of x of t. That is nothing but y of omega by x of omega with the zero initial conditions. That is very, very important. So simple, the transfer function of LTI system is dependent with h of omega, and it is defined as the ratio of Fourier transform of the output signal to the Fourier transform of the input signal. Simply it is nothing but the ratio of output to the input in frequency domain. So I am considering frequency domain. In the frequency domain, the output is y of omega and the input is x of omega. The ratio of output to the input, that is y of omega by x of omega, will give the transfer function h of omega. Or simply the transfer function h of omega is nothing but the Fourier transform of impulse function h of t. Here the transfer function h of omega is nothing but the Fourier transform of impulse function or impulse response, not impulse function, impulse response h of t. The transfer function h of omega is nothing but the Fourier transform of impulse response. Fourier transform of impulse response, that is h of t. Impulse response h of t. Okay. Now h of omega, here I am representing the transfer function with h of omega. This transfer function h of omega is a complex quantity. Complex quantity having magnitude and phase. It is having both magnitude and phase. So I can represent the complex quantity h of omega as mod of h of omega into e power j theta of omega. That is magnitude into some phase. Magnitude and phase. Magnitude is mod of h of omega, e power j theta omega. Theta omega is the phase. So the transfer function in frequency domain, the transfer function, this transfer function h of omega in the frequency domain is also called frequency response. Is also called frequency response. This frequency response is nothing but the sum of amplitude response and phase response. It is a combination of amplitude response and phase response. The sum of amplitude response and phase response will give the frequency response, and the amplitude response will get by mod of h of omega, and the phase response will get by theta of omega, simply angle of h of omega. So this is the amplitude response and this is the phase response. Okay, so there I got the amplitude response. So we can get the amplitude response and phase response. Using both of those, we will get the frequency response. See, in frequency domain, the transfer function h of omega equal to y of omega by x of omega. See, so y of omega will be equal to h of omega into x of omega. H of omega into x of omega. That is the transfer function into the Fourier transform of the input signal. X of omega will give the Fourier transform of the output signal, that is y of omega. From this we can write y of omega equal to h of omega into x of omega. Now go for the mod magnitude. So mod of y of omega equal to mod of h of omega into mod of x of omega. So if you go for the magnitude of the output, that is mod of y of omega, it will give the magnitude of the h of omega into magnitude of x of omega. If you go for the phase, so this is magnitude and this is phase, that is angle of the output, angle of y of omega equal to angle of h of omega plus angle of x of omega, that is angle of this h of omega plus angle of x of omega. This will give the phase of the output signal, this will give the magnitude of the output signal, this is the output signal. Okay, here this h of omega has conjugate symmetry property. This h of omega satisfies the conjugate symmetry property. So you all know the conjugate symmetry property, that is h of minus omega equal to h star of omega. So conjugate symmetry property, nothing but h of omega will be equal to h of minus omega. H of minus omega will be equal to h star of omega, or simply h star of conjugate h star of omega will be equal to h of minus omega. From that, mod of h of minus omega, mod of h of minus omega equal to mod of h of omega, that is magnitude of h of minus omega is same as magnitude of h of omega, that is the magnitudes are same, magnitude response are same for h of minus omega and h of omega. Come to the phase, angle of h of minus omega will be equal to minus of angle of h of omega. Angle of h of omega, that is phase of h of omega will be equal to minus of angle of h of omega minus of phase of h of omega. So that phase is a difference. So the difference is at a phase and the magnitudes are same, because this h of omega has the conjugate symmetry property. Based on that we can get the magnitudes of the both are same, but the phase will change as phase of h of minus omega equal to minus of h of phase of h of omega, or angle of h of minus omega equal to minus angle of h of omega. Okay, so this is based on the property, conjugate symmetry property, that is h of omega has conjugate symmetry property. Or simply this h of omega, already said that this h of omega, the transfer function is nothing but the Fourier transform of impulse response. Fourier transform of impulse response. The Fourier transform of h of t will give the transfer function h of omega. Now how can I get the impulse response? So the impulse response is nothing but the inverse Fourier transform of transfer function. Impulse response h of t can be obtained by inverse Fourier transform of the transfer function. Inverse Fourier transform of the transfer function. So h of t equal to f inverse of h of omega. So from this, if I know the impulse response, I can get the transfer function, or if I know the transfer function, I can get the impulse response by going for the inverse Fourier transform. Okay, now transfer function of a system in S domain. Now I go for the transfer function of a system in S domain. Up to now, I explained the transfer function of a system in frequency domain. Now, if I go for the transfer function of a system in S domain, I have to go for Laplace transform. In frequency domain, I use the Fourier transform. In S domain, I will use the Laplace transform. The concept is same. Simply here I have represented with the h of omega transfer function. In S domain, I will represent the transfer function with h of s. H of s. So say h of s equal to y of s by x of s. That is the transfer function in S domain is represented with h of s, and it is defined as a ratio of Laplace transform of the output signal to the Laplace transform of the input signal. Output signal is y of t. For that I have to find out the Laplace transform, that is y of s. Input signal is x of t. For that I have to find out the Laplace transform, that is x of s. The ratio of Laplace transform of the output signal to the Laplace transform of the input signal will give the transfer function of the system in S domain. Or simply we can get the transfer function of a system in S domain by using the Laplace transform of the impulse response. Laplace transform of the impulse response. So L of h of t. By this also I can find out the transfer function in S domain. So if I know the transfer function in S domain, h of s, then I can get the impulse response. So I can obtain the impulse response h of t by considering the inverse Laplace transform of the transfer function. Inverse Laplace transform of the transfer function, that is h of s. So h of t equal to L inverse of h of s. So in an S domain, if I know the transfer function, then I can get the impulse response h of t by considering the inverse Laplace transform of the transfer function h of s. Okay, so the explanation is same. So first I explained with respect to the frequency domain, and at last I explained with the respect to the S domain. So in frequency domain I will use the Fourier transform. In S domain I will use the Laplace transform. And the last, h of omega is the transfer function in frequency domain. H of s is the transfer function in S domain. One is the transfer function in frequency domain, another one is the transfer function in S domain. Now see, the transfer function in S domain, h of s is known already. By using the Laplace transform, I got the output of the Laplace transform, and I got the input of the Laplace transform, I got the transfer function h of s. If the transfer function in S domain, h of s is known, I know this value, then the transfer function in the frequency domain, h of omega, can be found by replacing s in h of s by j omega. Just by replacing s with j omega, s by j omega, I can get the transfer function in frequency domain from the transfer function in S domain. Here, if I know the transfer function in S domain, h of s, I can get the transfer function in frequency domain, that is h of omega, just by replacing s in h of s by j omega. So in h of s, replace s with j omega, replace s by j omega, then I get the transfer function in frequency domain. Simply, if I know the transfer function in S domain, I can get the transfer function in frequency domain just by replacing s by j omega in h of s. Okay, this is regarding the transfer function with respect to frequency domain and with respect to S domain, and the transfer function relation of frequency domain and S domain. Okay, so this is completely about transfer function of an LTI system. Okay, see, simple here h of omega. Okay, so if I need the transfer function of h of omega, I can get y of omega by x of omega. I need a h of s, transfer function h of s, I can get y of s by x of s. That is the ratio of output to the input in frequency domain or in S domain. Okay, so this is a complete explanation about transfer function. Okay, so here I completed two topics, that is unit step response and transfer function of an LTI system. Okay, so with this I am finishing today's class. Okay, I will continue the topics in the next class. Thank you one and all.